everyone, ready for more confidence interval practice? In this video, we're going to use the t-distribution to do our confidence interval construction. And we're going to talk about where the t-distribution comes from and when it's appropriate to use t-scores instead of z-scores to calculate those confidence intervals. All right, let's get started. English statistician William Gossett from Guinness Beer was the one that invented what we call the Students T-distribution. And we use the Students T-distribution when we aren't aware of the population standard deviation, but we want to calculate a confidence interval. I'm going to link the video that explains this in more detail. I definitely want you to watch it for review. In his work as a statistician at Guinness Beer, Gossett found taking big samples really tedious, and he wanted to invent a new way to do statistical work without having to take massive samples and use the normal distribution. However, Guinness did have a company policy in the 1900s that you weren't allowed to sign any academic papers you wrote with your own name. So instead, whenever William Gossett was doing statistical work, he always signed his papers as student, which is why we call the t-distribution Students T-distribution. It's our way of thanking William Gossett. The Students T-distribution is visually very similar to the standard normal distribution. See, the mean is at 0 and it's symmetrical about this average. It has that nice curvy bell shape. But you can see that with the Students T-distribution, there's more probability under the curve towards what we call the tails of the distribution. So it looks fatter or thicker at the ends of the distribution. That means there's more probability in the tails of the Students T-distribution. What's cool about the Students T-distribution is the exact shape varies depending on your degrees of freedom. So as your degrees of freedom, we're going to abbreviate that as DF throughout the course. As DF increases, which is dependent on your sample size, so as the degrees of freedom increases, as your sample size increases, your Students T-distribution is going to change. And as it increases, it's going to become more and more like the standard normal distribution. So you don't need to know the population mean or the population standard deviation to use this to calculate confidence intervals. I wanted to show a comparative graph for you so that you can understand how the normal distribution and the t-distributions at different degrees of freedom actually look next to each other. So let's compare the z-distribution to two t-distributions with ends around 30 and then smaller than 30. So as you can see, all three of these distributions are symmetrical around 0, so the mean is 0. And they all have a kind of curved shape. So the z-distribution, or the standard normal curve, is this blue, very peaked distribution. It's the tallest one. Most of the probability is here in the center, and it has very little probability here in the tails of the distribution. Now, very close to the z-distribution is the t-distribution. As your n increases, your degrees of freedom increase, and this, see, you can see this is the red t-distribution here with an n close to 30. It's very similar. It's not exactly like the z-distribution, but it's very similar, and it has a little more probability in the tails than the z-distribution does. Now, a t-distribution with an n smaller than 30 is here visually represented by this green curve. As you can see, it has less probability in the center, and it has even more probability here in the tails. So you can see it has a rounder shape instead of that bell curve shape with an n smaller than 30. Ideally, when we're using a t-distribution, our n is close to or larger than 30, so that the t-distribution better approximates the z-distribution. Calculating a t-score is really easy. This should look somewhat familiar. This is a lot like calculating a z-score. Your t-score is denoted by t, and all you do is take your x-bar, you subtract mu, and then you divide it by s, that's the standard deviation of your sample, divided by the square root of n, which is your sample size. Now, Bogner has another app for this. Just like we've been using the Bogner app for the standard normal curve, there's another app invented by Bogner that has a t-distribution calculator. So save these links. This is your bit link, bit.ly/B Ognar capital T. And here's the direct link for you to save if you want. You use this app in a way that's very similar to our standard normal app. First, you're going to enter your degrees of freedom into the white box. Then you're going to enter your alpha here in the red box. And what will appear in the blue box is your T-score. Now you can use the T-distribution when you don't have the population standard deviation, and the process looks nearly identical to how we use our Z-distribution to calculate error bounds. If the population standard deviation is not known, remember your error bound will use a T-score. So you take the T-score and you multiply it by the sample standard deviation divided by the square root of your sample size. We use degrees of freedom to help us find our T-score. So we take our sample size n and we subtract 1. And our S is our sample standard deviation. The format for a confidence interval doesn't change. Once we calculate that error bound, we just subtract it from our mean, and then we add it to our mean, and that gives us our confidence interval. Here's how we notate the T-distribution. We write a capital T, and we say it approximates the T-distribution for a particular degrees of freedom, so T sub df, where df equals number in our sample size minus 1. So for example, if we have a sample size of n equals 20 items, our degrees of freedom for this calculation are n minus 1, which is 20 minus 1, which is 19. So we write the distribution as capital T approximates lowercase t, 19. In our course materials for this module, I've given you a chart that helps you organize all of the information for confidence interval problems, and then you follow through the flow chart. So you'll organize your information, your X bar, your confidence level as a percent and as a proportion. You identify your alpha, your population standard deviation if you're given it, and the sample standard deviation if you're given it. Sometimes you'll be given a list of values from a sample, and you can easily use an online calculator or a hand calculator to calculate the mean and sample standard deviation for the problem. Now, the big question is whether or not you have the population standard deviation, written like this. If you do have the population standard deviation, follow down this side of the chart. You'll want to calculate the standard error of the mean using that population standard deviation, and this is the formula, so you'll calculate that. And then you'll use the Bognar app that has z-scores, the z-score normal distribution Bognar applet, and then you calculate the error bound, which is your z-score multiplied by the standard error of the mean. Or if you don't have the standard deviation of the population, you either have or you've calculated the sample standard deviation S. So you'll go down this side of the flow chart. So you'll calculate the standard error of the mean but using S, using the formula S divided by the square root of n. So you'll have that value here. You'll go to your Bognar T-score applet, and that's bit.ly/B Ognar capital T. And you're going to find the appropriate T-score to use for your problem. You're going to calculate the error bound by multiplying your T-score by the standard error of the mean using this calculation, using S, your sample standard deviation. Once you complete these steps, calculating your confidence interval is the same no matter whether you're using T-scores or Z-scores. Your confidence interval is your lower bound, upper bound. It's a range symmetrical about the mean, in which the true population mean probably falls within a certain percentage of certainty. So X bar minus your error bound, X bar plus your error bound, and you write it in this formula. And then here's a reminder of the sentence that we expect you to use in this course to explain your confidence interval. Of course, you don't include the words in the parentheses. This is just a reminder of what you use to fill in the blanks. We can say with blank % confidence that the true population of your item among your population falls between your lower bound value and your upper bound value, and make sure that you include your units. So let's do a Students T-distribution practice problem. In this practice problem, we have a random survey of enrollment at 35 community colleges across the United States. I'm not going to read all of the numbers at you, but here are the enrollment figures for each of those 35 community colleges. We're told to assume that the underlying population is normal. So look at this given problem. Do we know the population standard deviation? We don't even know the population mean in this case either, so we don't have any population metrics. I know that you could Google this about United States community colleges, but we have to work with what the problem gives us. So we don't know the average enrollment of all community colleges across the United States, and we definitely don't know the population standard deviation of enrollment at community colleges across the United States. So the thing that we have to do is maybe a little bit annoying, but we have to calculate the mean and the sample standard deviation by hand. Now, of course, I'm giving away a little bit of a trick. You could copy all of these numbers and you could enter them into a standard deviation calculator online. Remember, you're not taking a standard deviation of a population, you're taking it of a sample because we're just doing a random survey of 35 community colleges. That's a sample. I used an online calculator, and my X-bar, the mean of the sample as given, was as follows: 8,628.74. And our sample standard deviation is as follows: 6,943.88. So what was our n? That's the number in our sample, so that's 35. Now what is n minus 1? That's 35 minus 1, so that's 34, which equals our degrees of freedom that we're going to use with our t-distribution. Now it asks us to define the variables x and x-bar in words. So we know that x is the enrollment at community colleges. We know that x-bar is the sampling distribution of the means. For this problem, we have to figure out whether it's appropriate to use a z-distribution or a t-distribution. Well, since the population standard deviation is unknown, we have to use a t-distribution, so that means we need to use t-scores. All right, so now we're going to calculate a 95% confidence interval for the population mean enrollment at community colleges in the United States. All right, our first job is to figure out our t-score. So I used the Bogner T app on my phone, and I put my results up here so you could see. I entered my degrees of freedom, which is n minus 1, which is 34, so I first entered this. Then I made sure to select this option that distributes the probability of alpha between the two tails, and I entered my alpha. If we have a 95% confidence interval as a proportion, that's 0.95, so that means our alpha is 1 minus 0.95, which is 0.05. And then when I click away, I get the appropriate t-score, which in this case is 2.03. So we would say that our mean is somewhere here, 8,629, approximately right here. Now let's calculate our error bound. Here's the calculation. So I simplify this and I get the following answer. So we know that our error bound is 2,381.09. How do we then create our confidence interval? I'm going to go up here because there's a little space. We need to take x-bar minus our EBM, then our x-bar plus our EBM. So 8,628.74 minus 2,381.09 is, and 8,628.74 plus our error bound of 2,381.09 is. So this means that we are 95% confident that the true population mean of enrollment at community colleges across the United States lies between 6,247.65 students and 11,009.83 students. Now, as a final question, what will happen to the error bound and confidence interval if 500 community colleges were surveyed, and why? Well, if we increase our sample size from 35 to 500, that means that we will increase this denominator, which will make this fraction smaller. So as we increase our sample size, that means we're going to be making our error bound smaller and smaller. This makes sense. We know about the law of large numbers that we get closer and closer to our population means and standard deviations when we take larger sample sizes. So it follows that our confidence intervals will be smaller, more accurate, and close to the actual population mean, so it'll be a narrower confidence interval as we increase our sample size. So again, we have our top 3 takeaways from this video. It's never comprehensive, but it's just a good reminder of what we've covered. We want to keep practicing and making sense of this visual. If we don't know the population standard deviation, if the population standard deviation is unknown, we use this error-bound formula that has the t-score multiplied by our sample standard deviation divided by our sample size. And again, the only way to get good at confidence intervals is to practice with our practice problems, so keep up the good work on our homework. All right, everybody, thanks so much for tuning in, and I'll catch you in the next video.